In this video, I'm going to talk about blood type compatibilities. Blood type compatibility is important when performing blood transfusions. So compatibility between the donor and the recipient is important for recipient prognosis. Blood type compatibility between a mother and her fetus is also important to fetal health. Blood type incompatibilities are driven by an immune reaction against foreign bodies, namely foreign bodies on an incompatible donor's blood. So to understand blood type compatibility and incompatibility, we have to start by talking about antibodies. So I'll just introduce antibodies really quickly. So antibodies are produced by B cells, which are important immune cells that are partially responsible for generating long-term immunity, cellular memory against previously encountered pathogens. So produced by B cells. Antibodies are not alive. They are chemical weapons. They're little proteins produced by B cells. B cells are alive, antibodies are not. And so antibodies are to B cells as a sniper rifle is to an assassin, right? So the weapon itself is not alive, it's utilized by a living organism, in this case a B cell. So we can say that this is a B cell, and what B cells do is they spit out these little chemical weapons called antibodies into the body fluids to fight disease. So antibodies are responsible for identifying foreign bodies, and foreign bodies that enter your body are assumed to be pathogenic. So whatever the body, if you're invaded by an unfamiliar molecule, substance, your immune system treats that new molecule as if it were part of a pathogen, a pathogenic invasion. Okay. So antibodies are responsible for identifying foreign bodies, and they assume that these foreign bodies are pathogenic. So antibodies are produced in response to infection, or in the case of incompatible blood transfusions, it's perceived infection. So if you are given blood by an incompatible donor, your immune system, your B cells, will start generating antibodies to attack that blood. So antibodies are produced in response to infection or perceived infection, right? Because this isn't a perfect system. These B cells are not alive. They're programmed. They're programmed to have a response that is correct most of the time. But we didn't evolve with blood transfusions being typical. So we evolved so that the B cells would create these antibodies to attack anything foreign, because foreign things are usually bacteria and viruses invading our bodies. We didn't evolve with blood transfusions being typical. So produced in response to infection or perceived infection. They identify foreign bodies. There are a few different ways that antibodies fight disease, and we won't get too deeply into that in this video, but I'll just list a few important things. So antibodies, once bound, they can neutralize toxins and pathogens. They can neutralize toxins and pathogens. They can target a toxin or pathogen for destruction. Target, we'll just say foreign body for destruction. And another important thing that comes up with blood typing in a lab or blood compatibility is agglutination. So there's this fancy word, agglutination. And what that really means is clumping up. So clumping up of many toxic or pathogenic particles in one place. And agglutination, or the clumping up of a bunch of toxic particles or pathogenic particles, that is just to like hold, the antibodies are involved in wrangling up all of these toxins or pathogens into one place so that it's easier for the immune cells to come along and destroy all of those toxic or pathogenic molecules or particles or whatever. So the antibodies will bind to a whole bunch of these foreign particles, bind them all up in one place so that they're more easily cleared from the body, essentially. Right. Now, B cells produce antibodies that are specialized to target specific toxic or pathogenic molecules. So these antibodies have very unique and specialized receptor shapes on them. So the spot on the antibody that binds is unique and targeted to a specific toxin or a specific pathogen. So, and this is due to the shape of the receptor on the antibody, the chemistry of the receptor on the antibody. So shape and chemistry match between the receptor site on the antibody and a specific pathogen or toxin. Once a pathogen or a toxin binds to an antibody like a key in its lock, an immune response will be activated, and you'll get this immune cascade that is initiated to attack the foreign particles. Okay, so antibodies are designed to target specific pathogens or toxins. Oops. And once an antibody binds its foreign particle that it's designed to fit, right? An immune response is activated. Now, these cells are programmed in our early childhood, in infancy, and even actually in utero, to not produce antibodies that will attack our own bodies. Our antibodies are not going to attack our own organs, are not going to attack our own blood. If they do, that's called an immune disorder, an autoimmune disorder, right? When our immune system attacks our own body, that's the definition of an autoimmune disorder. But most of the time, this programming happens correctly. Most of the time, our B cells get correctly programmed to not generate antibodies that target our own bodies. So this means that we will not attack blood that is like ours. Our antibodies will not attack blood from donors that's like our own blood, our own native blood. Now, blood types that are different from our own might elicit an immune response, but it kind of depends. If an immune response is activated, the donor's blood, so let's say you have this transfusion and the donor had an incompatible blood type to the recipient, the blood recipient. So this will activate an immune response. This means that the donor's blood is targeted for destruction, and so you lose some of the donor's red blood cells that were meant for the recipient. But the bigger problem is the agglutination, which I had underlined here. The clumping up of the donor's blood will create blood clots that are too large to pass through the small vessels that feed the recipient's organs. So now the recipient of this incompatible blood, their own immune system is attacking the blood, causing agglutination, causing clumping. The blood can no longer fit. These blood clots blockade the passage of blood through organs, the essential organs, and this can lead to multi-organ system failure, which can result in death to the recipient. So it's really important to be able to identify whether a donor's blood, the blood from a particular donor, is compatible with the blood of the recipient. Now, another place where blood compatibility can be important is between a mother and a fetus growing in her womb. When a mother's immune system attacks her growing baby's blood due to blood type incompatibilities between mother and the fetus, the result is it can be fetal anemia, it can cause brain damage, and it can cause death to the fetus. We now have drugs that can protect the baby from the mother's antibodies in the majority of cases. When determining if a blood type is compatible, you have to consider whether the donor or fetal blood is introducing anything new or anything unfamiliar to the immune systems of either the recipient or the mother. New and unfamiliar molecules are assumed by B cells to be pathogenic. And so the B cells will produce antibodies that attack anything that's new and unfamiliar, which means you need to remember what molecules are found on the surfaces of these different blood types, which is covered in my previous videos. So let's start by looking at the ABO blood types. Now, the ABO blood type system is not really an important source for incompatibilities between a mother and her fetus. There is a slight increase in miscarriage rates when a mother and her fetus are incompatible in the ABO blood groups, but it's not a very strong effect. However, the ABO blood groups are a very common source of blood type incompatibilities when it comes to blood transfusions. So we will start here, and I want to start by saying that whenever a donor and recipient have the same blood type, they're always compatible. When a donor and a recipient have different blood types, sometimes they are compatible and sometimes they are not. So in other words, not all differences in blood types result in blood incompatibilities. To determine compatibility between a blood donor and a blood recipient, you have to know the blood type of the donor and the blood type of the recipient, and then you have to determine whether the donor is introducing something new to the recipient. It's the recipient's immune system that we have to appease. So let's start with a donor with blood type A. And remember, if this donor is blood type A, they have, so this is a red blood cell, and from I'll just use the symbols from my previous videos on blood typing. We're just so blood type A has this molecule, this glycoprotein that we call glycoprotein A, found all around the surface of the red blood cells. And that's why this person is called blood type A, because they have glycoprotein A on their red blood cells. And I've been drawing glycoprotein A like this. Now let's say that this particular recipient has a different blood type B. And so that means that the surfaces of the recipient's own red blood cells have glycoprotein B, which I've been drawing in my prior videos like this. So it's a different shape, right? It's an unfamiliar shape. So, first question, what is unfamiliar from the donor to the recipient? So the directionality here matters. It's from the donor. We're looking here. What's on the donor's blood that is unfamiliar to the recipient? Well, it's glycoprotein A, right? Glycoprotein A. So there's something unfamiliar. So are they compatible? No. The only way the blood types would be compatible is if the donor was providing nothing new. So let's look at another example. This one was pretty simple, right? You had different blood type and it's incompatible. But what if we looked at it this way? What if we said the donor had blood type A? So they're red blood cells, red blood cell, RBC for short. The red blood cells have this glycoprotein A on the surface. And now let's say that this recipient is type AB. So a person with blood type AB, so what's on this person's red blood cells? Well, they have both glycoprotein A and glycoprotein B. So they have the A glycoprotein, but they also have the B glycoprotein. So now let's look at this question. What is unfamiliar from the donor to the recipient? These two people have different blood types. The donor is blood type A, the recipient is blood type AB. But is the donor providing anything new? No. There's nothing unfamiliar. Nothing unfamiliar. Why? Because the donor has glycoprotein A. The recipient also has glycoprotein A. The recipient's immune system has been trained in early childhood, infancy, and in utero to accept glycoprotein A is normal because it is found on the recipient's very own red blood cells. So is glycoprotein B, but you don't get an attack for not having something. You just get an attack for introducing something different or new or unfamiliar. Glycoprotein A is familiar. Recipient already has glycoprotein A on their red blood cells, so there's nothing unfamiliar in the donor's blood. There's not going to be an immune attack against the donor's blood. So are they compatible? Yes. Okay, so that's an example of how a donor and a recipient can have two different blood types and yet still be compatible. But the direction of donation matters. So let's reverse this. What happens if the donor had blood type AB? So here's the red blood cells of the donor. They have both glycoprotein A and glycoprotein B, which I've been drawing in these ways. Okay. And let's say the recipient is A. So we've just flipped it. So in the last one, we said that the donor was A and the recipient AB. Now we have the donor AB and the recipient A. Now in the last scenario, the blood types were compatible for transfusion. But what if we switch which one was the donor and which one was the recipient? What happens now? Well, now let's ask our question again. What is unfamiliar from the donor to the recipient? Well, let's look at the donor's blood. They have glycoprotein A. The recipient also has glycoprotein A. So the recipient is familiar with glycoprotein A. Glycoprotein A is familiar. But the donor also has glycoprotein B. And does the recipient have glycoprotein B in their blood? No. So the recipient's immune system has not been trained to accept glycoprotein B because the recipient has never seen glycoprotein B before this blood transfusion. Glycoprotein B is foreign. It looks like a pathogen to the recipient's immune system. So what's unfamiliar? This one. This rounded one. Glycoprotein B is unfamiliar. You have something unfamiliar in the donor's blood. Is it compatible? No. The recipient's immune system is going to attack the donor's blood because of the B glycoprotein. Presence of a familiar A glycoprotein is not going to fix that. The immune system the programming is fairly simple. Anything that has not been seen before will be attacked. It doesn't matter if it's in conjunction with something familiar. It has to be that way because all living things, pathogens included, have a lot of familiar molecules on them. Doesn't mean that they're not pathogens. It's the presence of something unfamiliar that is problematic. So glycoprotein B is unfamiliar. These blood types are not compatible. So the directionality matters. It matters who is the donor and who is the recipient. And so you can see that a donor, an A donor can give to an AB recipient, because the A donation is familiar. But an AB donor cannot give to an A recipient because the B component of the AB is unfamiliar to the A recipient. So let's look at two others. I want to bring in blood type O in here. So let's look at an AB donor to an O recipient. So here's a potential AB donor with both the A and B glycoprotein on the surfaces of these red blood cells. And O, remember, means no A and no B. What is unfamiliar from the donor? Well, O doesn't have glycoprotein A, and the O recipient doesn't have glycoprotein B. Both A and B are unfamiliar. Glycoprotein A and glycoprotein B. It's all unfamiliar because people who are type O don't have any of those glycoproteins. So people who are type O can only receive from other O's. So no, these blood types these are not compatible for transfusion. How about in the reverse? Because we know that directionality matters. So here's the type O red blood cell. I've not been writing this in here. RBC for red blood cell. All right, so you have the O red blood cell in the donor. And let's say you have an AB recipient. So recipient has the A and B glycoproteins on the surface. I'm just doing this super quickly so I don't bore you. My coloring job's not so great. All right, so now we ask again, what is unfamiliar from the donor to the recipient? Well, O doesn't have any of these molecules. When it comes to the ABO blood system, there's nothing there. You don't get an immune response to nothing. You only get an immune response to something that's unfamiliar. So because the O blood type is clean when it comes to this particular glycoprotein, it doesn't elicit an immune response in anybody. This is why O is considered the universal donor. Because O doesn't have any of these glycoproteins, there's nothing on O that's offensive to anybody's immune system. It's clean, nothing for the antibodies to attach to, nothing for antibodies to attack. So O is the universal donor. Type AB is the universal receiver, because a person who has their bodies developed with A and B glycoproteins, so everything's familiar. So anyway, in this case, nothing unfamiliar. And so yes, it's compatible. The donation is compatible in this direction. So that's just a few of the possible donor-recipient combinations for ABO blood groups. So now let's start this whole thing over with the RHD blood group system, blood type system. So remember the positive or negative at the end of a person's blood type, like A positive, A negative. Remember that the positive and negative refers to the presence or absence of the RHD antigen or the RHD glycoprotein. Now, the RHD blood type system can result in blood type incompatibilities for transfusions, but it can also be a real problem for blood type incompatibilities between a mother and her fetus. The thing is that most people are RHD positive. And so most people are compatible with each other. 85% of the population is RHD positive. So let's take a look. Now we're going to do the same system. And remember, now when you're talking about a blood donation, you're worried about the recipient's, appeasing the recipient's immune system. So you want to know what the donor is providing that the recipient is unfamiliar with. When you're talking about blood type compatibilities between a mother and her fetus, it's the mother's immune system who you have to appease. So in that case, the fetus would be a little bit more like the donor, and the mother would be a little bit more like the recipient. So let's take a look at two scenarios. We'll start out with the donor being RHD negative. So we'll just put the negative sign there, and the recipient being positive. And I'll put in parentheses here the fetus and the mother. So if the donor or if the fetus is blood type negative and the mother is blood type positive, RHD positive, what does that differ? Because, you know, like if they have the same blood type, then it's fine automatically. So if it's different in this way, what is unfamiliar from the donor to the recipient? Well, let's look at what these red blood cells look like. So here's the red blood cell. Remember, this is a completely different blood system governed by a different gene than the ABO blood groups. So we're considering this completely separately from the ABO blood groups. So if the mother is RHD positive, like 85% of the population, she's going to have the RHD glycoprotein, which I've been drawing in my videos like that. RHD negative just means that glycoprotein's not there, so I'm not going to draw anything for the fetal blood group, blood type in this one. All right, so now we ask our question, what is unfamiliar from the donor to the recipient? Or you could ask, what is unfamiliar from the fetus to the mother? Well, in this case, the donor or fetus has nothing unfamiliar because like blood type O, there's nothing there. So if there's nothing there, then there's nothing unfamiliar. So we'll just write nothing unfamiliar. Is this compatible? Well, yes. As long as there's nothing unfamiliar, it's compatible. But now let's look at different blood types in the reverse direction, in the opposite direction. Let's say that the fetus or the donor is RHD positive. So in this case, the fetus has the RHD glycoprotein on the surface. We can also call this an antigen, an antibody generating molecule. So they have the RHD antigen or the RHD glycoprotein. And let's now say that it is the recipient or the mother who's negative, RHD negative, so doesn't have the glycoprotein. Well, now let's ask our question. What's unfamiliar from the donor to the recipient? Or what's unfamiliar from the fetus to the mother? Well, let's look at the donor fetus row here. This is unfamiliar. The RHD antigen is unfamiliar. The mother doesn't have that. The recipient doesn't have that. Never seen it before. That's unfamiliar. That's going to elicit an immune response. So I'll just draw that here. This is the RHD antigen, or we'll call it glycoprotein. That's what we've been calling it. So is this compatible? No. Nope. This is going to cause problems in a transfusion or for mother-fetal compatibility. So mothers who are RHD negative need special monitoring during their pregnancies, especially if there's some question as to whether the child might be RHD positive, and that depends on the father's blood type. Now, the first time a woman is pregnant, the first time an RHD negative woman is pregnant with an Rh positive fetus, there are rarely problems because it takes the mother's immune system time to generate a reaction to the RHD, the unfamiliar RHD antigen in the fetus. And also fetuses create signals to suppress the mother's immune system while growing inside her. And then that's just a normal part of pregnancy. Pregnancy involves immune suppression so that the mother's immune system doesn't attack this foreign body growing in her womb. But after her first pregnancy with an RHD positive baby, and after her first exposure to that RHD antigen, she is going to start developing antibodies that attack that RHD antigen. And so her second pregnancy with an RHD positive baby, those antibodies are going to be there. They're going to travel through the umbilical cord into the baby and destroy the baby's red blood cells, as if the red blood cells of the baby were pathogenic. And this causes what's known as erythroblastosis fetalis. Erythroblastosis fetalis. You can think of that as the erythrocytes, that's red blood cells, blastosis. So you think of it as blasting, the mother's immune system is blasting the red blood cells or the erythrocytes of the fetus. Erythroblastosis fetalis, or fetalis, sorry. So treatments include intrauterine blood transfusions to replace the damaged blood cells in the fetus, early emergency deliveries to get the baby out of there as soon as is possible, and drugs like Rogam. So there's a few different brands, but drugs like Rogam suppress the maternal immune responses to the RhD positive blood.